All right, we're back with chapter 7, the energy equation, and we're going to do section 7.7 this time. And basically, we're going to um, use a combination of the three equations that we've been working with, the continuity equation, the momentum equation, and the energy equation to actually calculate the head loss for a sudden expansion. This section really is called transitions, and it's about using these three equations, these three formulations of the Reynolds transport theorem to look at transitions in flow. So let's go ahead and forward ahead to this section. It's way up here. Slide 51. Here we go. And let's get into this. So the purpose of this section is to illustrate how the energy and momentum and continuity equations all can be used together. This is important because it provides a nice review of these concepts that we've been dealing with and how to use all of these concepts together. So we have this situation here where we have what's called an abrupt transition. The flow comes out of one diameter of pipe here, D1, rapidly and instantaneously really into a different diameter. This might be a pipe that's fit into another pipe, and a good example of this might be like an inner tube or something like that, where this would be the valve and this would be the tube. And so this is the air expanding, and we choose our control volume such that we have a surface right here where even though this is D2, that diameter D2, it's just past the inner diameter, the smaller diameter, and then we go way down the other end of this pipe here where the flow becomes uniform again, and we avoid all this turbulence. And so, what is the energy equation in this situation? Well, it's we don't have a pump and we don't have a turbine, so it's just P1 gamma plus alpha 1 V1 squared bar over 2G plus Z1. This equals P2 over gamma plus alpha 2 V2 bar 2 over 2G plus Z2. And we do, in fact, have the head loss in here. This is going to be important. That's what we're looking for. So what is the momentum equation? If we go back to this equation here, and we are back to the picture here and look at this, we can see that we need to, a couple of things we need to do. We need to account for the pressure pushing in here on this area A2, and we've got another pressure pushing in here. And this would be P2 and this would be P1. But they're both pushing on the same area. Notice that it's both area 2, pi d2 squared, or pi over 4 d2 squared. And so in addition, we have the force of gravity here that's pointing down, and we're going to decompose that into two vectors. This vector, because we're interested in the component here that's in the direction of the flow, S. So this is the component in the S direction, and it's going to be equal to basically mg times this sine of alpha. So we'll use that here in a second to look at the sum of the forces on there. So we've got these two pressure forces, and we've got this this gravity force. But when we write this, when we write this down in terms of the momentum equation, remember we've got the sum of the forces. That's kind of a bad summation sign, but it's the sum of the forces, and that's going to equal, as we remember, since there's no momentum accumulation, that's going to be equal to the outflows, which is m dot v2 minus the inflow, which is m dot v1. And so we can rewrite this equation now. We've got P1A2, the pressure coming into the left-hand side, minus P2A2, the pressure coming into the other side, but in the negative direction. Remember, these are all in the S direction. And this, our gravity term, actually in the correct units, turns out to be gamma A2L. This is just M. Remember, this is rho G. Gamma equals rho G. and this equals mg over v. But we've just written down the area as A2L, where L is the length of the controlled volume, and of course we have the sign of alpha because it's the component in the s direction. And we're going to express these m dots in terms of the velocity. They're rho VA. So this whole thing is going to equal rho V2 squared A2 minus rho V1 squared A2. Correct? I'm sorry, that's not actually right. Let's do that correctly. That's V1 squared A1. Yes. And so, so what we have to do now to simplify this equation is just divide through by gamma A2. And we can see that we get an interesting equation. I'm going to try to write it down here in the bottom so I can keep things straight. But what we're going to have is P1 over gamma minus P2 over gamma. This is starting to look familiar, isn't it? And over here, we're just going to have minus L times the sine of alpha, but we can note that L times the sine of alpha is actually just the difference of this height minus this height, or these two reference heights. We'll call them Z1 and Z2. So this even looks even more familiar because now we have minus Z2 minus Z1, which is looking pretty similar here. And this is going to equal, and I'm going to have to kind of squeeze this in here, but it's V2 squared divided by G minus V1 squared divided by G times A1 over A2. And if we, so let's just hang on to this equation right now, okay? This is going to be important. I'll rewrite it here in a second because we want to combine that here with the continuity equation. Since this is an incompressible fluid, usually we assume that we just have V1 A1 and V2 A2 for this. We could put the rho's in here, right? We can keep those in there, but for an incompressible fluid, they cancel out. So this is our normal equation. And as we've been noting, the velocities in this case are equal to the mean velocities. Again, these are actually bars as well. So we can just assume that these bars are removed when these things are equal. These are equal to 1. So the book shows how we end up with two equations here. Let me just go ahead and write those on a new sheet. So we end up with this equation here, P1 gamma minus P2 gamma minus, this was the momentum equation that we wrote down before, and that's going to equal V2 squared over G, not 2G, just G, V1 squared over G, and A1 over A2. This is the one that I squeezed at the bottom of the page a couple times ago. But we also have this equation here from the energy equation. So this was momentum, just call that mom, and this is energy. And we had P1 gamma. We moved the P over from the other side. These are kind of looking familiar. And we're going to have, actually I have, this is actually minus Z2. So this is minus, we can write it this way, plus Z1 minus Z2. I think I actually had a sign error right here. No, I got it right. Okay, and so this is going to be the same as this. This term is actually the same as this term here. But on the right hand side now we are going to have the head loss, and we're going to have plus V2 squared over 2G plus V1 squared over 2G. Now, that means that we can set this thing by combination of the momentum and energy equations, and using the continuity equation for this, we can get this equation right here. We're going to have V2 squared, I'll just do this in detail here, over G minus V1 squared over G, and for A1 over 2, we're actually going to replace that with V2 over V1, because that is from continuity, and that whole thing is going to equal HL plus V2 squared over 2G plus V1 squared over 2G. Through some algebra, we can move HL over to the side, and we can actually show that this whole thing equals V1 squared minus V2, V1 minus V2 squared. Now note that this has a cross term in it, and that's, if we do some gymnastics here, some algebraic gymnastics, we can see that these four terms here actually can be combined into this term here. And so this is looking a lot more like a head loss term. If we assume now that this volume actually empties out into the free atmosphere and into, say, a reservoir, if this dumps out into a reservoir, which is a very large tank of water, then we can assume that V2 equals 0, which the book does. And what we have is our familiar term for the head loss, which is going to be basically the velocity, V1 in this case, squared over 2G. So this is why, one of the reasons why we've been using this form for the head loss. So what we've done in this section, section 7, is we've used a combination of the energy equation, the momentum equation, and the continuity equation. All of these applied to this problem of a transition and an abrupt expansion in a pipe to show that the head loss in this case, if the water spills out into a large reservoir, is going to be equal to V squared over 2G. So that was the purpose. There's also, here's the final equation from the book. And so remember, forces on transitions, we can look at these by applying a combination of the momentum equation, energy equation, and the flow rate, or the continuity equation. And the book actually has a great example. I'm just going to quickly write down what the equations of this are. This, let me get rid of this. This is applying the energy and momentum equations to find the force on a pipe contraction. So the pipe contraction looks something like this. Let's see, we've got a pipe contraction here. It's a bad diagram. But we've got a contraction here, and we're looking for the force here in the x direction that's required to hold this in place if, say, we had some sort of maybe a weld or something that's holding this little nozzle piece onto this pipe. So that's what basically the picture in the book looks like. It's a little bit prettier than that. And so it's a 30 centimeter pipe, carries water at 10 C and 250 kilopascals. So this is pressurized here, P1, at a rate, a Q of 0.707 meter cube per second flow rate. And the pipe contracts down 10 centimeters to 20 centimeters, and the head loss is given by this term. And V2 is the velocity here in the constriction. So what horizontal force is required to hold this into place? And we're going to assume that the kinetic energy factors are 1 at both the inlet and outlet. And so what I'm going to do is just quickly write down the equations for this. This is similar to what we did before. So the momentum equation becomes P1A1 minus P2A2. You've got these pressure forces on either end plus the resulting force to hold it in place. These are m dot v2, very similar to what we did before back in chapter 6 and in just the previous problem. And this is reduced to fx equals rho q. We're plugging in qa for q for VA, and this is going to be V2 minus V1. And moving the pressures over to the other side, we have P2A2 minus P1A1. So that's the momentum equation. The energy equation, if we let alpha 1 and alpha 2 equal to 1, and note that it's a horizontal pipe, so Z1 equals Z2, and I'll just, whoops, that's a 2, and alpha 1 equals alpha 2 equals 1. And no pump, no turbine, so those are both equal to 0. We do have the head loss, however, but if we write this equation out and rearrange it, we get that the pressure at P2 is going to be equal to P1 minus gamma times V2 squared over 2G minus V1 squared over 2G plus the head loss, which is given by that equation. So we can actually calculate the head loss, and if you go through the equation just real quickly, that was 0.1 times V2 squared over 2G, and we know we can get the velocities from Q. So when we do that, V1 turns out to be 10 meters per second squared if you do the math or look at the example in the book, and this is 22.5 meters per second. I'm not second squared, just second meter per second. And so if we plug this value in up here, right into this equation, we get a head loss of 2.58 meters. All right, so that we were also that gives us the head loss here. But of course, now we can use that to plug into this equation here to get the pressure. And when we do that, it turns out the pressure, if we calculate it, the pressure at point 2 turns out to be 21.6 kilopascals. And remember, we were given the pressure at point 1 in the statement of the problem, that was a pressurized pipe with a 250 kilopascals at P1. All right, so now that we have P1 and P2, and we have Q, and we have V2 and V1, we can go back to this equation now. F of x equals rho Q V2 minus V1. This is all from the force or the momentum equation plus P2 A2 minus P1 A1. And if we plug in here and work it out, f of x is going to be equal to, turns out to be 81.6 kilonewtons. And it's going to be acting towards the left to counteract the force of the fluid on the contraction. So that's a way of dealing with these, basically combining the energy, momentum, and continuity equations to look at a complex problem where we actually have head loss. Remember, the key here is that the statement of the problem has head loss. This was different when we were dealing with the problems before in chapter 6 where we weren't able to do this. So that's it for chapter 7 on transitions, and so we're able to now combine all 3 of these equations to solve more difficult problems. Okay, thanks.